n, it's f1 minus 1 plus f1 minus 2. So you're recursively calling the Fibonacci procedure in this second line here, fn equal to fn minus 1 plus fn minus 2. Okay? Now it's important to note that whenever you're defining recursion or recursive algorithm, you have to have what is known as, ultimately there should be what is known as a base case. Okay? So if you do not have base case, that's where you don't see the self-reference. If there is no base case, it's going to go into infinite loop. We have actually seen that example. I asked you a question, hey, what happens here? Right? So then it goes into an infinite loop. Okay. Now I think it looks like everyone is able to hear me just fine. I don't see anything in the chat which suggests otherwise. If anyone still has difficulty hearing me, just put it in the chat and we'll see what we can do. Okay, we considered an example, factorial, very simple. As you can see here in the C code, I'm assuming you are able to read it well. I put it in presentation mode there. That's all there is to it for C, a small piece of code for factorial. If I is less than or equal to 1, you return 1, otherwise you return I star factorial I minus 1. So if I were to do a factorial 3, right? So I think we took that example last time, but I'll repeat that one more time here. If I say, I'll write here, so let me go back to, I will put it in a slightly, okay. So if I were to take, let us say, factorial 3, so that means I is equal to 3. Let's say I'm doing I equal to 3. So if I do I equal to 3, I'm just writing here. I equal to 3. So we go to factorial, unprime integer I is 3. If I is less than or equal to 1, it is 1. So it's going to go to return I star. So if I go here, so this piece of code would look like what? It's going to look like 3 star factorial 3 minus 1 is 2. Got it? Pretty straightforward, right? Once you get a hang of it. So now, since this function is called again, so then it goes to what happens then, this gets broken down into 3 star. Then next time when you call factorial, I is equal to 2. So this is going to be factorial. Okay. 2 minus I star, right? So you'll say 3 star, 2 star, sorry. Factorial 2 minus 1, that will become 1. So when it goes to 1, then it goes, checks that if I less than or equal to 1, it is 1. So it's going to return 1. It's going to be 3 star, 2 star, 1. Okay? That's where it basically ends. So you got factorial 3, then it becomes 3 star, 2 star, 1. That is 6. So the program is correct. So this is how I can test the data. Let me pause here. Any questions? Okay. Let me go there. So what we did was we said, hey, go do your trace, right? Remember I said after the class you can go try to do that. That is exactly what I have done here, right? So in the previous slide, I basically traced the code there in front of you there. Okay. Okay. And we talked about Fibonacci series, and again I said that go and execute this, right? I gave the code, I said you execute it and let me know the result, right? I do not know if you had a chance to do that. And similar lines here. There is a base case. If you see if I equal to 0, return 0. If I equal to 1, return 1. Those are the base cases. And then you have this return Fibonacci I minus 1 plus Fibonacci I minus 2. So if I were to take, let's say, same thing. If you apply the same thing, hey, if I equal to 3, then what happens, right? So you trace what I have done in the previous case, and then you get the value. Okay. So why do these recursive methods work? The way it works is, right, it goes back to understanding what happened inside the memory, right? Or the operating system, how this is being tracked inside your memory is what this is all about. Every time a function is called, okay, an activation record is placed on the stack. Now, what is a stack, right? So there are a bunch of new things coming up. So let's try to understand that one here, okay? Let me create a new slide here. And then I'm still, since I'm writing, I'm kind of putting it in a regular slide mode, not the presentation mode. So when you talk about this activation record, runtime stack, what is happening there, right? So that is what we're trying to understand. If I were to remove this one, let me put it here. Okay, so if you let's say you have a procedure F1 or function F1, okay, inside this let me just call it like this. Whenever you're writing program, you just immediately put the parentheses, right? So here you have F1 process, and then let's say inside this one, this function is calling F2. Okay? So that's another function. So that means you will have one more set of function there. And inside, and then to make this one a little bit readable, we'll put it like this. Okay? So you have F1 function, and then you have F2. And let's say for the sake of completeness, we'll put one more function here. And then you're calling F3. Okay. So what is happening inside the memory? Memory is nothing but a piece of, let me draw memory as a table here, okay, to show what is happening there. Okay. So let's see. Let's say I put, this is my memory. Remember, memory is nothing but a content, it's space, right, in RAM. That is memory. We're referring to RAM here, right? So here, the way the compiler builds your program and it compiles is, it starts creating these activation records on the stack, this memory stack. Nothing but a bunch of, let me actually put the name there. Give me a second. Why is it not coming? Give me a second. This is memory. Okay? Okay. Let me put something. So far, so good. Are you able to hear me well? Just put some response there. So in memory is nothing but space, right? So now what happens when you have F1, within F1, when F2 is called, so in memory you write that, you build the activation record for F2, and then we build activation record for activation record for F3, and so on. So what does activation record mean? Common sense, right? What it means is once you finish the function, you should know how to get back to where you stopped. Okay. So let's say here, before I called F2, let's say I had some variable I or int I. Int I equal to, let's say, 5. Okay. So before you call F, and then you call F2. So when F2 is done, when you come back here, I'm putting dots here, right? Your program should start executing from here, correct? Let's say I'll put something else here. Here I. Okay, and then let's say here, I'll say I can come back to J. So everyone knows this, right? From Computer Programming 101. Okay, in case you have not learned it, here is the first opportunity. I'm in F1 when I assign I equal to 5. So in memory, let's create one more line here. Let me put it there. We can insert. I want to insert one more record. I'm trying to do that. Font, no, that's fine. We can. Why I'm not able to insert another record? Okay. I don't want to do that. Okay, that's fine. Never mind. Even if I cannot insert another record here. So now, when I say activation record, there should be, actually let me call this activation record for F1. Then I go to F2. Then I go to similar thing, activation record for F3 and so on. Okay? So when I'm in F1, when I call F, I do integer I equal to 5 just before this activation record for F1. Then I'm calling F2. Okay? When I call F2, after I'm done, somewhere here at the end, I will have in memory, I would have J equal to 12. Okay, somewhere. But we are not there yet. We just call F2. So before I call F2, I save everything about F1. So what do I save about F1? Where is it stored? It's variables, etc. And if you can see the white on the right, not okay. So you have to keep track. Here is one, and then keep track of memory location will be on it. Okay. Everything in the F1 state, you have to save. That is what is the activation record. So that way, when you come out of the function, you know exactly where you have to continue from. So when you come out of F2 and then F3, ultimately you should continue from integer j equal to 12. All that information is saved. Okay? It's a little bit complicated for the purpose of this class, but just remember that I need to save the state space. Okay? Typically, when you take the operating systems class, we get into more details. Okay? How the memory is laid out. We have pages, what is the page size, or segments. So we talk about all of those things, and we talk about these things too in greater detail there. Okay. That's the activation record illustration. Okay, now let me go to the GCD. We discussed GCD to some extent, and then if I remember right, let me put in presentation mode so that way. Okay, you should be able to see this. Okay, so some faculty members asked me if I can trace it. We kind of traced it. Okay. My apologies for the size of the text because, oh, sorry. Okay, that should do it. Okay. So I traced it for you. To an extent, I said, hey, but you also trace it, right? I said, take the code. If I remember right, I think we took some two integers, right? What were they? I think it was like 170. A is 100, B is 70. And then we said, go through the lines all the way from 10 through and so on, right? So when we did that, we put how this formula works, right? Now, the key thing to note here is, right, this is just one way of computing GCD. Greatest common divisor. Between 100 and 70, the greatest common divisor is 10. Okay? And then this is one way of looking at it. There are two or three different ways of computing the GCD. Okay? But in this case, what we have done, we use recursion. Because since we are learning recursion, we use recursion. So as you can see here in line number 24, as long as A is not equal to B, right? So that is 100 and integer B is 70. Then based on the if condition, you call the GCD function again. But in the process of calling, the value is changing. Now it is not just GCD AB, it is GCD A minus B comma B. In the case of A greater than B. Okay? If A is not greater than B, then you do it GCD A comma B minus A. I think we traced it from 100 to 70, and I think 3-4 times we go through, then you would know that the value between the two, the GCD is 10. Okay? I'm looking at the video of Chaitanya here. Just show of hands. Have you traced it by yourself? That was one of the things that I asked you to do after the class. We covered the example. I traced it for 1 or 2 iterations. I can see the video of Chaitanya. You can raise hands if you have done it after the class. Did you trace this code? Okay. Has anyone traced this code? I'm putting that in the chat also. You can answer it in the chat. Okay. Pretty easy there. Okay. I think this is where kind of we said one of the things that you have to be careful when you are doing the recursive functions. There's a chance that it can go to an infinite loop. That's why you call it broken. So here I gave an example of a broken recursive function. So int x equal to broken factorial n minus 1. And then of course you say if n equal to 1, return 1, else return n star x. Okay. So I think we said, okay, what's wrong here? I wanted you to tell me what is wrong here in this piece of code. And you don't need to really get scared about the fact I call this as public static, right? That is the C++ syntax, but you can ignore public from space static for now. If you ignore that, it is still integer broken factorial int n. And everything else, think of it as a C function. Okay. So what is wrong here, right? So you have a broken factorial. If I say 2, you have broken factorial that I just shortcut it to BR fact. Okay. 2, 1, 0. What is happening there when you trace it? It is going through infinite loop. It never ends. Okay. So that if it never ends, then we call it what? If it never ends. It's broken, right? Basically, it does not terminate. So if you run this code, what would happen? you will see some fault. You know what that fault is? Faculty members are welcome to help here. There is something called, when you write some infinite loop stuff here, you get what is known as a segmentation fault. That's an operating system's concept. Remember, whenever you're calling a function, what are we doing? We are building an activation record in memory, right? So memory is still finite, right? It could be 1 gigabyte, but it's still finite, right? Memory is not infinite. So when you keep on writing activation records, at some point you run out of the space, correct? Then we get what is known as segmentation fault and core dump. The system crashes, basically. Very dangerous about using recursive algorithms. It's very easy to write an infinite loop and crash the system. Okay? So that's the reason why you need to always be very, very careful to ensure that you have a base condition which would allow you to come in, which would allow the program to stop once the base condition is reached. Okay? Here, the guy did not put the base condition. That was the problem with that. Okay. So I gave a little bit more explanation here. Right? So we do recursive call first before checking for the base condition. Okay? Right? Because the base condition, if n equal to 1, is return 1. Whereas before even you check the base condition, you are calling the factorial function here, right above that. So you would never get to if n equal to 1. So by switching these two, if n equal to 1, return 1. Okay? By putting that above the first statement, int x equal to broken factorial, you would not have the situation of an infinite loop. Okay? Very common mistake that programmers make when you are writing recursive functions. They forget the base condition, or when they do it, they put it after the recursive function is called. And then it would never execute that because it is recursively calling some function before the base condition is checked. Okay? So be aware of that. Okay. So when you are doing this recursive design, this is what you're doing here. Again, saying it in a different way one more time, right? So you'll have a base condition to begin with. Always have that in your brain. It should be hardwired. A recursive means, first thing I need to say, what is my base case? Base condition. Okay? Write that down first. First statement in the recursive procedure. Okay? Then you come up with the recursive cases that operate on smaller problems. Okay? In the case of factorial, all you're doing is you're taking n star factorial n minus 1. So that n is always coming down and down and down. Okay? Same thing with Fibonacci, right? The base conditions for Fibonacci are what? N equal to 0 or n equal to 1. Once you go past those two conditions, then you have we have factorial n minus 1 plus factorial n minus 2. That is the formula for that, right? Okay? And of course, big bold thing, base condition should always be checked before the recursive call. Okay, we beat it to death. Let's move on. So base condition is basically allowing you to end the recursion. Okay? Now when you have recursive call, you should change at least one of the parameters and make towards the base case. Okay? I'll skip the example there. By now you know how to write it. Okay? Some notes here about recursion. It's not an easy concept. A lot of people have a little bit of a challenge writing recursive algorithms. Okay? So what I call it as, once you practice enough on examples, you should be able to do that. Okay? As long as you remember base case and recursive case, then you are good. Okay? So here is some examples. Okay? So you are given a list. Remember we talked about linked list, right? Okay, you want to process the list. To process the list, in the case of list processing, you have to look at the base case. What is the base case? Hey, if current is null, then return false. Now, what do we have in list? Remember we talked about head, right? And then as you're traversing it, in the current variable called current, you always keep moving the head pointer. That's one way of looking at it. Seeing which element in the list is being looked at, that is your current. Now, if current is pointing to null, that means there is no list, right? Only once you do dynamic memory allocation, remember we did the malloc. The very first statement was to create at least one node. First, you need to do a malloc. Once you do that, you get one node. Then the base case there would be current would point ahead. Then it won't be null. Okay. So one condition is null. That means the no list exists. The other condition is if first item equals to the target, then return value because you're looking for some value there, right? Now, after those two base cases, then you do the recursive call. You say current dot next. Remember, next is what is pointing to the next node. Okay, and then you go into that recursion. I don't know if I have the code here. Let me check. Yeah, I don't think I put a code. Instead, what I did was I said, hey, do some exercise, right? I said, write a C program to find the nth Fibonacci number using recursion. Has anyone written this exercise? I didn't check the community. Has anyone written an exercise to find the nth Fibonacci number? You can say yes or no in the chat. I hope the question is clear. Has anyone written this exercise to find the nth Fibonacci number? Okay, each one of you knows what a Fibonacci number is now, right? Or is that a new concept for you folks? Okay, everyone is silent. Silence does not tell me anything whether you know what a Fibonacci number is or not. We covered examples too last class. So here the program is asking, hey, what is the nth Fibonacci number? And then I said, write it using recursion. Okay. Somebody said, okay, no one probably wrote it. Okay, no problem. But let me ask you another question. Did you look at the code for Fibonacci sequence that we discussed in the class? Did you review that from the slide deck that I gave you? You can answer one more time, SVCW. If you reviewed the code that I gave you, then this should be pretty straightforward to do that. Okay? Okay. So we'll come back to this exercise. I will not give you exercise yet. I wanted to cover a few more things, then we'll come back to that and we'll do some hands-on exercise. So that way this recursion would be hardwired into your brain once and for all. Okay? Now, when we do recursion, one quick question that comes up is, what is the difference between recursion versus iteration? Okay. As a rule, any recursive algorithm can be rewritten as an iterative algorithm. So to write an iterative algorithm, you will have some kind of a for loop, a non-iterative, iterative algorithm, not recursion. You'll have some kind of a for loop or a while loop, some kind of a looping condition to achieve the same effect as any recursive algorithm. Okay. A thing to note here is not all programming languages support recursion. Okay. Like COBOL or Fortran. You probably were not even born when we used to write code in COBOL and Fortran, but those languages don't support recursion. Okay. If you look at the list processing languages like Lisp or Prolog, I actually programmed in Lisp and Prolog a long time ago. You probably didn't hear about those languages in your life so far. But they rely heavily on recursion because those are mathematically oriented programming languages, and recursion is very common in math. Okay, some theory. Then, good exam question for you would be, how do I know whether I should do recursion or not recursion? Okay. So, the reality is, when you write an iterative loop, that is faster. When you do recursion, you will see some examples where the complexity, the time complexity, remember we talked about complexity in one of the lectures, right? How much time it takes for the program to execute. You will see, especially in my advanced class on data structures, that recursion leads to poor time complexity, meaning it takes more time. Then in those cases, you will have no choice but to write it as an iterative algorithm, where the time complexity is much more. I don't hear any static. Let me mute all of you one more time. You're already unmuted. Okay, I'm muting all of you. Yeah, audio is fine. Let me share my screen. Somebody took my screen away, so let me go to. I don't want anyone to share. I want the control to be with me. So, Jntuk, I'm taking the control away from you. I'm making myself the presenter. So I should be able to share my screen now. Okay, excellent. Okay, I just need to open the PowerPoint again. That was a very funny audio problem that I got. Never had that before. No idea what that was. Okay, give me a second. Oh, I need to look at my file here. Okay, opening the file and I'll share it shortly. Because you got a 3-minute break there, that is kind of nice. So I will put it in the presentation mode. Share. PowerPoint. Okay, got it. So the question then becomes is, do we want to do recursion or not do recursion, right? So as I told you, later on you will learn about recursion has some problems in terms of time complexity. So in the cases where the time complexity is bad compared to doing it non-recursive way, obviously we would use the non-recursive technique. Okay. So one of the classic examples that we get to show how bad recursion is, we use the Fibonacci sequence. Remember we saw the Fibonacci recursive procedure, right, in one of the slides here in the deck, where you keep calling Fibonacci n-1 plus Fibonacci n-2. So if you study the algorithm closely there, the same Fibonacci number is being computed every single time there is a recursion, which is very inefficient, right? If I already know what Fibonacci 3 is, and when I'm in a big recursive procedure, and every time I go to the next recursive procedure, I'm calculating Fibonacci and 3 again and again and again, that's inefficient algorithm. So you'll see some issues like that when you're using recursion. Okay? So, in the case of sorting, for example, okay, we do selection sort versus merge sort. Which one to choose? In this case, what you will notice is you will actually choose merge sort, which is a recursive algorithm. Selection sort is not really recursive. One we have seen is non-recursive, whereas when we see merge sort, in that case we'll actually use recursion. And it turns out to be okay in the case of merge sort. This section actually ends with a merge sort example. So hang on to your thoughts till we come there to see why merge sort makes sense, where we can use recursion. Okay. Factorial. When you're doing factorial n star, right? It's much easier to write a loop and it's much faster. Okay. There's no difference actually, if I'm not mistaken. Faculty member, you can correct me if I'm wrong. You can verify that there's really no advantage for the recursive version over a non-recursive version in the case of factorial. Okay. Binary search. We did binary search, if you recall from earlier classes, where we do how do we do a binary search? When we have an array, we go to the middle element. If middle element is what we are looking for, then we got the answer. Otherwise, we say go to the left side of the element if it is lower number, or go to the right side of the element if it is a higher number. And then we did that, so far we did that using non-recursion. We showed many examples, we showed non-recursion, right? So we'll again see which one would be easier between those two, whether it's recursion or non-recursion. Okay? If you look at the Fibonacci sequence, as we mentioned here, the last one is, look at the beautiful way we have it in the code, right? Log Fibonacci integer n equal to 0 return 1, n equal to 1 return 1. Otherwise, you return fib n minus 1 plus fib n minus 2. So here is a recursion, right? You are calling the same function. Function is fib, and you're doing it. It looks beautiful when you write recursive procedure, but what happens when you start tracing it? Okay, here is the trace. I keep telling you, hey, trace your code. This is an example of tracing code again. I showed you enough traces, but here is one more example. So for fib 5, if you take 5 as a number, you call fib 4, then you call fib 3. Okay? Right? 5, 4, 3. Now when you call fib 4, fib is short for Fibonacci. According to the procedure, you call fib 3 and fib 2. Okay? Now if you go down further and you say when you are in fib 4, when you call fib 3, you are going to call fib 2 and fib 1. Okay? And of course, for fib 2 to complete the argument, we call fib 0 and fib 1, which are the base cases. See, you have to, as long as you arrive at the base cases, you are good. We know that there is no infinite loop here, and you will be fine. Okay? I'm just turning on my video to see, you are able to see my video also now. I'm managing the bandwidth. That's why I didn't turn on the video so far. Okay? Now, what is happening here, if you look at this code here, the same fib numbers, okay, like fib 2, right? They are repeated and they are solved again and again, right? The trace shows here, right? If you look at fib 3, you are calling fib 2, right? Again, when you go inside fib 3, you are calling fib 2. Multiple times, the same fib is called, and multiple times, the same fib 2 is calculated. Okay? That is what this is saying. So the sub-problem of fib 2, they are solved again and again. The reason why they are solved again and again, it's solved once before. If we save that state before, then we don't have to worry about solving it again, right? So if you can somehow figure out how to store this partial solutions, then it saves us a lot of time. Whereas since we don't do it in the case of fib the way we have written, right, it would have exponential time complexity. That is the reason why when you use recursion in Fibonacci, it doesn't help. because you're calculating it over and over again. And remember, you all know what exponential is, right? So, so you don't want to be exponential. Remember I said it's better to be log, if not linear, or of the order of n. You don't want it to be exponential. Okay? So, again, a little bit theoretical. Your second year, first semester students, unless you trace it, you would not appreciate it. Okay? Okay. So now, when you write it as non-recursive Fibonacci, right, where you're creating an array of size n and fill with values starting from 1 up to going to n, right? We simply write a loop, okay? And you always only remember 2 Fibonacci values, and then you compute the next one. Okay, let me show you an example of that. Okay. Here is a Fibonacci. So if n is less than 2, we are returning 1. Okay. Otherwise, what you're doing, you are basically doing the for loop there, right, where you're always calculating the previous flip plus second previous flip. Okay. So I eliminated, there is no recursion here. So when you count the instruction, remember we learned how to count instructions, right? So, and then we said we eliminate the constant factors and look at the for loop. And in this case, for loop is what it's basically of the order of n, right? As n tends to infinity, correct? So all of a sudden, your order, the time complexity is of the order of n, whatever that n value is. Instead of the recursive Fibonacci, where the time complexity is basically exponential, here you came up with a order of n, which is much better. Okay. So that is one of the things that you need to be aware of when you're writing algorithms, right? Time complexity. Now, what is the reality in the industry? Most of the 99.99% of the cases, we don't use recursion. Recursion is fantastic on a piece of paper. Mathematics-wise, the code looks very elegant, right? But from a time complexity viewpoint, most of the algorithms tend to be iterative in nature as opposed to recursive. Okay. Where do we use recursion? Having said that, right, we do use recursion somewhere, and that is where we get into these algorithms called divide and conquer algorithms. Classic cases are binary search and merge sort. Okay. So let's look at I think I have an example of one of merge sort for sure. So let's keep going to that. Okay. So what is divide and conquer? We know what divide and conquer is, right? Classic strategy that the British Empire used in India long time ago. We learned that in our historical texts. Similar thing here. Okay. We divide the problem into smaller instances, right? And then we conquer, meaning we solve the smaller instances recursively. And then we combine the solution. That is the third bullet which is important, right? We combine the solutions to obtain the solution for the original problem. Okay? So that is what we do in a lot of, I did about half a dozen different divide and conquer strategies in my advanced data structures class. Okay? But here we'll take a look at one or two examples. So here is the general strategy. You have n, which is whatever size was given. Okay? If it is a really small n, then you solve it directly. Otherwise, you divide it into sub-problems here. The L is divided into L1 to Lk. And we solve for each of the sub-problems. We solve them. Okay? Then you combine, as you can see just before return, you combine those sub-solutions. Now again, it looks all very theoretical to you, right? So we need to say concrete example of divide and conquer. So let's look at that now. Okay? Okay. Before we look at the example, just a little bit more notes on divide and conquer. Simplest approach, as they say, very efficient. Efficient meaning in terms of time complexity. And here are the examples: merge sort, quick sort, selection sort. Okay. Okay. Let me look at the example directly. I'm skipping one or two slides here. Yeah. So here is a classic divide and conquer pictorially, right? What did we say in binary search? We said that we will look at the midpoint. So we are finding the midpoint of the array. If what we are looking for is at the midpoint, then you are done. Okay. If it is smaller value, then look at the first half. So that means we have totally eliminated the second half. But if the value is larger, then you look on the second half. That means you have totally eliminated the first half. That is what we are doing, right? We are dividing the array. That is exactly what we are doing here, divide and conquer. So dividing the array, you are looking for the solution. And then you start focusing on only the half of the array where the solution is likely to be found. Okay. Now the same thing, when you do it in a non-recursive way, you can see the code here, integer bin search. Bin search is binary search. It is taking target, saying, hey, look for the number 25 in this particular array. Target is 25. Okay. So you are keeping track of the first element and you are keeping track of the last element, pointers, right? You need to know what is the starting point and what is the ending point. Okay. While starting point is less than or equal to the ending point, you calculate the mid, first plus last divided by 2. Okay. So if the array size is 10, first is pointing to 0, last is pointing to 9, correct? 0 to 9. Remember, we start, that's the reason why you see array dot length minus 1. First is less than or equal to last, right? So if I have to put it here, you see, yeah, 0 is less than or equal to 9 for a 10 element array. Okay? Then you get mid equal to first plus last divided by 2. So it's a 10 element array. So in this case, I'm saying, let's say mid is equal to 5. Let's assume that. Remember, it's integer division, right? Rounding it off. Let's say I do that. Now, if at element array 5, that is in computer language terms, it's array 4. If you find the target, let's say the target value is 10. Let's assume target value is 10. Right? So if you find at array 4 or fifth element is array 4, target value 10 is found, you're done. If not, what do you do? Okay? That is what the if statement is, right? You found it, you return. Okay? Now, if target is less than array mid, what happens? Let's say array mid is say 25, and you're looking for 10. 10 is less than 25. So then you move the last to mid minus 1. Because since it's a sorted array, it has to be less than that array 5, right? Or array 4. So you move the last. So now all of a sudden what happens? The last value would be, since we said array 4, the last value would now become 3. Okay? So now you search between 0 and 3, and you will find it there and you return. Now if this else is not met, then it should be in the second half. So you move the first. So you at the end of each loop, you're either moving the first to the right or the last to the left. That is what you're doing here. Okay? And if the value is not found, you get return minus 1. Okay? That is how the binary search works. So you're always eliminating one half in every single iteration of the loop. Okay? Okay. Now the same thing written in binary code, int binary search. So you need first, last, and target, remember, right? Without first and last and what value you're looking for, you would not be able to solve the problem, right? So you still have the same if statement, first is less than or equal to last. Still have the same statement for the mid is first plus last divided by 2. Still have the same statement, this one. If target equal to array mid, you found it, you return. Now, in the next statement is where you will see the change. If target is less than mid, then you call the binary search function again, where the last has now changed to mid minus 1. I will show you the contrast one more time. This is very important. Here you had a while statement here. Do you see the while statement in the recursive algorithm? No. Because we don't loop through the array. What we do is, we just do this condition where you did the if target. This is what you did, right? So you do that condition here, if target. You found the solution, great. If not, you are going to call the same function with the new value of either mid minus 1, that is last, right? Or mid plus 1, where the first is moved to mid plus 1. Okay? Depending on whether the target value is less than the mid or not. Okay? And then you are calling them. It's an interesting statement here. See this one here? No loop here, right? It's a recursive call. But don't think about it if it confuses you. Okay? It's a very funny statement because not many students, recursion is not intuitive for a lot of students, even though the reality is recursion is there all around us, whether it's in nature, the molecular structures that we talk about in chemistry and all that. There's a beautiful recursion to all of those patterns. Okay? But when it comes to computer programming, it's a little bit challenging for people to write, but it's actually not that confusing in my opinion. Once you get a hang of it, write one or two programs, then it becomes easy. Okay. Okay. Let me. I think I wanted to give you some exercises. Okay. Let me stop here for a second. Questions, comments, because I'm going to get into a merge sort algorithm now. That's the reason. Okay. How many of you find a recursion simple enough to understand? You can put something in the chat here. You understand recursion, but you prefer non-recursion algorithms, whatever, right? You can put it there while I continue with the rest of the slides, okay? Because I want you to practice this one in the class after I finish that today. So one of the algorithms that I told you is, we'll come back to that later. That's the reason why I'm doing it now. That is a merge sort. Because without really understanding recursion, without understanding lists, linked lists and all that in greater detail, it's hard to understand merge sort. Now you have enough knowledge base to understand it. So remember, what are we doing here? We are basically applying what is known as a divide and conquer strategy. Okay? And then we'll continue to call. This is, by the way, sorry, let me take one step back. What are we doing here? We are merging and sorting. That means the input to this program is an unsorted array. Okay. And we learn the techniques of sorting arrays like bubble sort, selection sort, right? Different types of sorts like that. We even looked at quick sort, right? So this is another classic way of doing it, because the reason why merge sort is popular is the time complexity is the best out of all of those things. Actually, quick sort is a better time complexity. Okay. Use the divide and conquer strategy. You have an unsorted array. So to do the divide and conquer and then moving fast in increments of half of the array, you need to keep track of first and last. We saw that too in the algorithm earlier, right? In all the algorithms, when you do bin search and all that, you have first and last. So you need to have the same first and last here. Okay? So once you divide it, then you take the first half, which is shown on the left side, and you sort that recursively by using merge sort. Okay? The mid element, of course, is sorted by default, right? Because it is already one element. There is nothing to sort for one element. Then the right side of the array, you sort recursively. So at some point when you go through this one, you get a sorted array on both sides. Once you get sorted everything at level, you merge all of them. So that's why you call it merge sort. So you sort first and merge ultimately. So you're going top down in terms of breaking it first. Then when everything is sorted, then you start merging bottom up. Okay? Now here is an algorithm which is, by the way, this is the type of algorithm where unless you go execute it in your favorite language, you would not appreciate it, okay? So algorithm says input is an array E, and we are given first and last, okay? And the output is the same algorithm except all the numbers are sorted. And from an algorithm viewpoint, you can see here is the algorithm of function name. It takes the element E array. This is nothing but your array. The input is array. You need to know what is the first element of the array, what index rather, right? You need to know what the last index is. Okay. Then you are saying if first is less than last. Okay. You are going to come to the midpoint. Okay. After you get the midpoint, you are going to call recursively the merge sort. Right? E first up to midpoint, and then you call the second merge sort, E mid plus 1 last. If you go back to the picture here, that's what we are doing here. You calculate the midpoint. On the left side, you call the merge sort. On the right side, you call the merge sort. Okay? Look at this piece of code here. These two merge sort. Okay? And after you do that, you merge first, mid, and last. So you're merging both the sorted halves. That is, these two are sorted, you're applying the merge sort. So conceptually, that's what merge sort is doing. Okay? So we are going to trace merge sort in this class for the rest of the time. So that way you understand that, right? But before you do that, let's look at the rest of the slides, and then we'll come back to the exercise in just a minute or two. Okay? Why is merge sort? This is some other class, advanced classes, where you will see that merge sort has a nice n log n algorithm, basically, which is much better than what was the bubble sort? How many of you remember bubble sort time complexity? Was bubble sort n squared? Right? These were n squared algorithms, if you remember. Selection sort, insertion sort, and bubble sort. If you go back and look at your notes, you will see that those were n squared. Okay? So n log n is better than n squared. Right? If n equal to 100, 100 square is a humongous number. Whereas n is 100 log n. Log n of 100 is what? 2 raised to 5, right? 5 or 6, at most 7. Log of 100, right, to the base 2 is what? 2 raised to 6 is 64. 2 raised to 7 is 128. So it's between 6 and 7. Let me even say 7. N is 10. 100. 100 times 7 is 700. That is the order of the algorithm, the time complexity of merge sort. Where 100 squared is substantially more than 700, right? So we use for all these unsorted arrays typically merge sort. It turns out in many cases, at least on paper, quicksort has a better efficiency, better results than merge sort. Okay? At least in theoretical analysis. But I have read a lot of studies where all kinds of data, they have really not noticed any big difference between merge sort and quicksort. Okay, just as an aside. Very rare cases you will see that quicksort really is better than merge sort. But on paper it certainly is better. Okay, so this kind of basically shows how you're kind of basically taking two sequences, okay, and then you want to create one big sorted sequence in C. So he gave some kind of steps here. You can ignore that for now, because when you do your tracing, you will understand it better. Okay. Again, showing what the algorithm itself is, right? For when you are given two sequences, how that works. We'll not come up to that stage yet. Okay. So that is so much for recursion. I wanted to bring a merge sort in the context of recursion after I introduce you to recursion. Okay. To summarize recursion, it's a natural way to solve many problems. Okay. And the merge sort is a classic example where recursion really works very nicely. Okay. The opposite of that is this one, where recursion stinks when it comes to time complexity in the case of Fibonacci. Okay. And then to use recursion out is really a design approach, right? You can think recursively, as most often we say in the industry say, hey, do the design recursively on a piece of paper. But because it becomes easier to explain to people, but when you implement it non-recursively. So think recursively, implement non-recursively. That is the modus operandi for most of the programmers in the industry. Okay. Now to do recursion, it's important to remember that you need to identify a base case and then the recursive part. Because if you do not have the base case, what happens? It's going to go into infinite loop 99.99% of the time. Okay? Okay. So, rest of the time, we are going to do the following. Okay? We have about 10 minutes, or you can, since I started the class almost 10 minutes late, if you are all free, you can spend another 10 minutes more. Okay. What I want to do is I want to go to this exercise. Where was the exercise? Okay, let me see the exercise. Okay. Faculty members, please facilitate this exercise in the classroom for the remaining time. Next class, when we come back to next class, we'll be talking about stacks and queues. Let me share one document here before you do that. Data structures. So if I'm going to share my screen here. So if you look at the syllabus here, we pretty much covered all aspects in Unit 1. Because in Unit 1, they kind of talked about recursion, right? So we covered all aspects of Unit 1. We talked about factorial, GCD, Fibonacci. We didn't come to Tower F and I'll give that more as an exercise for you. Okay? Sorting techniques, we covered most of them. A couple of them I have not covered yet. But I have covered pretty much everything here. Bubble sort, quick sort, selection sort, insertion sort. I did not cover radix or radix sort. We'll look into that. I covered merge. Okay? When we're talking about this section, it becomes very easy now. With this foundation, section 2 would become very easy for you once we get to it. Okay? And then if you see the amount of things that we have covered in terms of linked lists, this entire slide deck had more than half of the slide deck was linked lists, right? I give you enough examples. So in case you're wondering when we come to Unit 3, I just did it in an order in which I thought it would make sense. The way syllabus is written, it's not my syllabus, but I reserve the right to rearrange them in such a way that I introduce some of the concepts earlier. So that's what we did. So when we come to Unit 3, it will be a breeze for you because you already know linked lists. Okay? Great. Let me stop this one. Let me go back to PowerPoint. Please take a note of it. Write it down on a piece of paper, groups of 2. Trace merge sort on this list. Write down the list first. Then I put the slide on merge sort. Okay? So let me put it in the chat for you, otherwise that way it's easy. Trace it on the merge sort, okay? Okay, put it in the chat. So what do we do in merge sort? First thing we do is, we do first, I'm putting in the chat again, or I can put it on the slide. And I'll put it in the chat. Okay? Pay attention, chat. We say first plus last in parentheses. Let me put parentheses. Mathematically correct. Correct. Divide by 2. Correct? So take this list, divide by 2. It has how many elements? 1, 2, 3, 4, 5, 6, 7, 8. Okay? So you divide by 2. That's what the merge sort algorithm is, right? Let me go here. I put the list in the chat for you. Okay? Here's the algorithm, right? That is the array. You know the first element and the last element. It's first less than last. So when you trace it, in the case of our array, what is the value of first? First equal to array start at 0, right? And last is 0, 1, 2, 3, 4, 5, 6, 7. Okay, last is equal to 7. I'm doing the first trace for you. First plus last divide by 2. So mid equal to, what is the mid value? Chakra floor antama, ceiling antama, next integer keltanki. 7 divided by 2, 3.5. Typically you round it off to the next integer, which is equal to 4. Okay? So, fourth element, 0, 1, 2, 3, 4. That is fourth element is 7. Okay? So you trace it like that. You say 7. Then, going back to this one here, that's what we did here. First plus last divided by 2. Then you have the left side sub-array and then the right side sub-array. Got it? So you put the left side sub-array and the right side sub-array. So if I have to go back to this list here again, so this is how it looks like. So 0, 1, 2, 3, 4. So you got 7 as element by itself. Merge sort left. Left low, what are the elements that you will have? 8, 3, 2, 9. 8, 3, 2, 9. And then merge sort right. You will have 1, 5, 4. Okay? That is after the end of trace 1. Now do the trace 2. Apply the same thing for this one and for this one. Okay? Should not take more than 5 minutes for you to trace it. Okay? Then when you finish all of those things, what do you do at the end? You merge them back in the order, reverse order. Okay? Okay, everyone understand the problem? Anyone has any questions there? So trace that. I put the values there. So the algorithm, I'll just open the algorithm and put it there for your convenience. Okay. Please take about 10 minutes to do that. If you really have to leave in 3 minutes, by all means you can leave, but come back to it after your classes and convince yourself that the merge sort works based on the algorithm that I gave you there. In terms of an assignment, a lot of you were very enthusiastic in executing your bubble sort and selection sort and all of those things using C programming language, and you put that in the community. So I want you to go and implement the merge sort algorithm in C programming and put it in the community for us. The program. Here I'm just showing you the algorithm. Next week we can take a look at your program too. Okay. I'm done for today, but I will hang around when you're tracing it. And again, my apologies for the delay today. As I told you, I was just sleeping off, and then I just woke up a little bit late. And I put this in the community, as you know, the slide deck, and I'm assuming that all of you have downloaded it. Question for faculty. I received the rosters from a couple of people. Please send your rosters. Only a few people. Out of all these colleges, I received it. I received from a few of them. I don't remember on top of my head who sent that. I know Jntuk Moocs was one. I think it was DMS, I think, that sent me a roster. Another one. Only 2 or 3 of them sent it. Others, please do send the rosters. In the rosters, what I want is name of the student, name of student. Okay, and then I said the email ID of the student. And one more column, student enrolled in community. Student, one second, enrolled in community. Yes or no answer. Those of you who have not enrolled in the community, then we can pressure them into, I mistyped enrolled. Okay. I want, if you can send those rosters soon, that will be helpful. That's the assignment for the faculty members. Okay. I did not give any quote today. Chakravarti, if you are still there, why don't you put a nice quote for all of us? Our students, if you have any nice quote, we'll end the class with a nice quote. So I need a nice quote. Please put it here. I do see Chaitanya doing the trace. DMS, I think I see the video. Doing the trace. Has anyone finished tracing? Tracing merge sort, I mean. The problem is, right, unless you trace or unless you write some algorithm in the class, you would not understand these concepts. So that's why you always have to have some exercises like that in a classroom to assimilate the material. This is not the type of material where you just learn by listening to a lecture, right? You have to do hands-on there. If you finish tracing, just put it in the chat that you finished it.
Misra. Okay. Sure.
JNTV video, the students are still there. JNTU Kakinada, I see the regular classroom completed. Okay. I know SVCW said completed. How many steps?
And then
Meaning like different paces, just out of curiosity. Oh, somebody shared a nice quote. Thank you very much. If your dreams don't scare you, they are not big enough. Oh my God, dreams have to be scary enough? I never knew that. But thanks for letting us know. Take up one idea, make that one idea your life. Isn't that what Abdul Kalam said, or who said that? Nice quote. Take up one idea, make that one idea your life. Of course, and in humorous way, it's like that one idea is to chase after one movie star, and you make that your life, right? Like right now, my favorite heroine is Anushka Sharma. So if I want to take up one idea is to meet her, then that I have to keep dreaming about her now. Swami Vivekananda, yeah, great man, great man. Yeah, thanks, Cindy, as always. Good. Any questions, comments? I know one one college finished the tracing. What about anyone else? Only one college completed, SVCW. They are super fast in this class. That's one thing I noticed, SVCW. JNTUV, in case you're still there, they're kind of beating you in most of these classes. JNTUV is a little bit less, they're a little bit less, what I should say. They're not less, somebody else is beating, so you should pick up the challenge and next class you should finish things faster than them. So far in all the MOOCs classes, JNTUV was always winning hands down. This class I see other colleges kind of are at the forefront. By the way, this is all only friendly competition. Huh? I'm not biased against anyone. I'm just instilling friendly competition so that we will all become better. Okay, if there are no more questions, I will sign off. If there are no more questions, I will sign off. I will put some other questions in the community. Secretary, thanks for pinging me on the chat. See you on Monday. Monday, Friday. Have a wonderful day, everyone. And what are the upcoming holidays? Chakravarti, if you know when is the next holiday, please let me know. So that way I don't have any surprises. I assume there is no more holiday before midterm.
Yes, sir.
Okay.
Sir, I want DMSS. I want DMSS VHCE College and Chaitanya College mentors to call me.
Okay. DMS and Chaitanya, please call Chakravarti Garu.
I'm giving my number, sir, in the chat.
Okay. I'll leave the chat open. వాళ్ళు ఇంకా రాస్టర్స్ పంపించలేదా? పంపించాలనుకున్నానే.
No, I have not received their list from DMSS HCE and Chaitanya College.
Okay. By the way, ఇప్పటివరకు మనకి we don't have a total idea about what are the total number of students, కదా?
Till now I have the idea, sir, excepting these two colleges. If they send the things, I can do it.
Okay. You can do that. Okay, perfect. DMS, and then you can put the two college names there in the chat. Just one more
DMS
time.
and Chaitanya Engineering.
DMS and Chaitanya. Okay. Great, you heard it. Chakravarti Garu is the boss who is running the show here, so we have to do it, I guess, once he says. Thanks, Sandy. I'll sign off now.
Good night, sir.
I'll